measured and also what we have already measured at optical, in the optical band. Okay, so intrinsic polarization. Well, we expect that the radiation emitted by the star surface layer, by the neutron star surface layers, is polarized because neutron stars do have a strong magnetic field. And the strong magnetic field acts in changing the photon particles cross-section, and so the way in which radiation interacts with matter. And second, because the presence of a strong magnetic field alters the electric and inverse magnetic permeability tensors, and thence affects the way in which radiation propagate in a cold plasma plus vacuum medium. And this is shown here by the structure of the wave equation. And of course, this is the inverse magnetic magnetic permeability tensor. This is the electric tensor. In general, radiation coming from a neutron star transverses a cold plasma plus vacuum medium, and which is magnetized. And in general, radiation is expected to be elliptically polarized. However, if the photon energy is much smaller than the electron cyclotron energy, the two normal modes of polarization are almost linearly polarized, and they are called the extraordinary or X and ordinary or O modes. This is a cartoon which shows how the electric field of the radiation oscillates, the direction in which the electric field of the radiation oscillates with respect to the plane made by the local direction of the magnetic field and the propagation vector k. The extraordinary photon has the electric field which oscillates perpendicular to the plane made by z or k and b, while the ordinary photon oscillates in the plane made by the propagation vector and by the local value of the magnetic field. The opacity properties of the two modes are dramatically different in the sense the O mode opacity is almost unaffected by the presence of the magnetic field, which means that the O mode, the ordinary photons, interact with matter as normal unpolarized light in absence of any magnetic field, while the X mode opacity is strongly reduced with respect to the unmagnetized case by a factor which, roughly speaking, for scattering, this is exactly the dependence goes like the photon frequency square divided by the electron cyclotron frequency square. So if omega is much less than omega c, the opacity is strongly suppressed. Of course, if talking about surface emission from neutron stars or surface emission from a neutron star which crosses a magnetosphere in which there are charges, the intrinsic polarization depends on the surface emission model that we think applies for our neutron stars, and of course also on the possible role of matter, of electrons which circulate in the magnetosphere. There are actually two basic models which we can think describe correctly, although we don't know which is the really correct one, the emission coming from the surface of a neutron star. Either we think that the neutron star surface is covered by a gaseous atmosphere, or the neutron star has a sort of condensed surface in the solid or maybe liquid phase. In this case, it is called a bare neutron star, and this bare neutron star is maybe covered by a thin hydrogen layer. There is a very nice review paper by Sasha Potekin on this. And the emission properties, of course, and the polarization properties strongly depend on the choice of the model, of course, and also on the local value of the magnetic field and on the temperature. If you know, because you selected the model also for the distribution of B and T on the surface besides the emission model, then you can calculate the polarization degree at the emission, the intrinsic polarization degree, simply by computing the difference between the flux in the X mode and the flux in the O mode and normalizing this to the total flux. Then if you would like to have an idea of how much the light coming from the surface of our neutron star is polarized, you can divide the surface into patches and sum up and up those which are in view at a certain phase. And of course, this will depend on the orientation of the neutron star and also on the angle which the neutron star makes, the neutron star spin axis makes with the dipole axis. So everything will depend on these two angles, which I call psi and chi. This is the neutron star spin axis, this is the magnetic axis, this is the line of sight. And of course the neutron star, come on, okay, is spinning and is showing different areas during the spin movement at the different phases. So here are two examples of what comes out from this kind of calculation. This is the intrinsic polarization as a function of the two geometrical angles Xi and Chi for the condensed surface. This is the same from a completely magnetized, magnetized, fully ionized hydrogen atmosphere. And you see, of course, that the intrinsic polarization is completely different in the two cases. I mean, the shape could be somehow similar in the two cases, but if you look at the absolute scale of the polarization degree, that's fairly different, as you can see. Okay? In this case, the intrinsic polarization is much higher than in the other case. Okay. What is the observed polarization signal we can expect once we know how to describe the intrinsic polarization? Well, let me just remind, this is a rather obvious point, that the polarization is most conveniently described, or better polarized radiation, is most conveniently described using the Stokes parameter. These are additive quantities, and of course the Stokes parameters, which are listed here, the intensity, total intensity, Q, U, and V, are expressed through the complex components of the electric field. And let me just point out that the normalized Stokes vector, so the vector made by Q, U, and V for linearly polarized radiation in the X and O mode is just written in very simple terms as 1, 0, 0 and minus 1, 0, 0 for the extraordinary and the ordinary mode respectively. I'm going quickly through this. The fundamental point one should recognize and bear in mind is that each photon is polarized in the ordinary or extraordinary mode, but it is so polarized with respect to a frame XYZ, which is defined by the propagation vector k and the local direction of B. Of course, as the photon propagates, the local frame XYZ changes if B varies. Of course, k remains always the same, because this is, of course, the line of sight direction. But if B changes, the local frame changes. So before one can add the Stokes parameter of the single photons to compute the polarization properties of the entire radiation, there is a very important operation that needs to be performed. One must rotate the Stokes parameter to bring them in the same reference frame, which is the polarimeter frame, which is defined by three axes, U, V, and W, where, of course, W is in the direction of the line of sight. Here is a cartoon which shows you through this drawing what I said before. Here are 2 points close to the neutron star surface. The direction of B is different in the two cases. K is, of course, the same. These two Ks are two parallel vectors. And if I build up the two reference frame, X prime, Y prime, and Z, X prime prime, Y prime prime, and Z, the two reference frame are different because, of course, the magnetic field is not the same. So what I need to do is to rotate the Stokes parameter by an angle alpha prime if I want to refer to the first point, or alpha prime prime if I want to refer to the second point. The rotation of the Stokes parameter intrinsically tends to produce a depolarization of radiation. So if you start with a source which emits, with a neutron star which emits from its surface 100% polarized radiation, just because the surface of the neutron star is not point-like and the magnetic field is changing direction along the surface, the radiation you observe will not be 100% polarized, because you need to rotate the Stokes parameters. Okay. So these are just the very simple formulas which relate the Stokes parameters in different frames, which describe the rotation of the Stokes parameters. In our case, They simplify to this form because for X and O photons only Q is different from 0, which is either +1 or -1. So, I mean, starting from this expression, one can derive very easily which is the total Q and the total U for radiation emitted in different points along the star surface. Okay. And of course it depends on alpha, and alpha will change according to the different positions on the neutron star surface or close to the neutron star surface. So, I mean, putting everything together, one can conclude that the polarization properties of neutron star emission are described by two parameters, by two observable quantities, the polarization fraction and the polarization angles that are quite simply related to the Stokes parameter Q and U. Pi L is simply the square root of Q square plus U square divided by the total intensity. If I use the normalized Stokes parameter, it's simply the square root of the sum of the squares of the normalized Stokes parameters. And of course, the polarization angle is 1/2 the arctangent of the ratio U over Q. And let me point out that there is just one case in which the observed polarization degree or polarization fraction and polarization angle coincide with the intrinsic ones. And this is the case in which the angle alpha I, which the magnetic field, which we need to rotate the Stokes parameter, is the same for all the points, as, for example, in the case in which the magnetic field is uniform. If not, as we expect around the neutron star or on the surface of the neutron star, the rotation must be accounted for. Of course, the rotation of the Stokes parameter is not the only effect which contributes to make the observed polarization signal different from the intrinsic one. The second very important one is that the magnetized vacuum which fills the space around a neutron star. I'm not considering in this case any contribution from matter, so it is a polarized vacuum. According to QED, this vacuum is polarized, so it's full of virtually plus and minus pairs because of the presence of a very strong magnetic field. The first consequence is that this modifies the dielectric and magnetic permeability tensor of the vacuum, which in this case behaves like a birefringent medium. And this can be actually seen by linearizing the wave equation, that is to say, using the geometric optics approximation. And if you do that, you obtain a set of ordinary differential equations which govern the evolution along the ray of the complex amplitude of the electric field of the wave. These are the vector A, which has component AX, AY, and AZ. And of course, this differential equation which governs the complex amplitude A of the magnetic field can be translated into a set of differential equations which govern the evolution along the ray of the Stokes parameters for photon which propagates along the ray in vacuo. And these are the three equations which describe the evolution of Q, U, and V, the three Stokes parameters. A few words about the different quantities which enter in these equations. K0 is just omega over c, the photon frequency, so this is the photon wave number. This quantity delta is proportional to b squared, and of course z is a coordinate along the ray. In order to see qualitatively how the Stokes parameters change along the ray, one should note that the evolution of the Stokes parameters is governed by two length scales. The first one, let me call LA, is simply 2 over K0 delta, and this is proportional to B minus 2 and the energy of the photon to the minus 1, and this is the characteristic length scale over which the Stokes parameter change. There is a second very important length scale which I call LB, which is simply B divided by the modulus of K times the divergence of B, the gradient of the modulus of B. And for a neutron stars with a dipole field, this is simply roughly the radial distance. And LB measures the length scale along which the magnetic field varies as the photon propagates away from the neutron stars. These two length scales, LA and LB, if you make them equal, they define a characteristic length at which the two are equal, and this radius, which is of the order of few times the neutron star radius, of course depends on the value of the magnetic field and the pole, it depends on the energy of the photon, is called the polarization limiting radius or adiabatic radius. And the condition LA equal LB, as I think is quite understandable, is a sort of divide for the way in which the Stokes parameters evolve in the magnetized vacuum. And this, I think, can be better seen from this cartoon. If LA is much smaller than LB, then we are in the so-called adiabatic region, and the photon polarization mode will follow immediately the direction of the local magnetic field. So a photon which was born as an extraordinary photon, say, will stay in the extraordinary photon mode because it evolves very quickly and it can adapt its polarization mode to the change of B, okay? Of course, as we move outside, then LA decreases, sorry, LB decreases and LA increases, and we enter the so-called intermediate region. And the intermediate region, it is still true that the photon electric field tends to follow the direction of B, but with some delay, so to speak. And finally, when LA is much larger than LB, in the external region, the direction of E will be frozen and will not follow the change in the direction of B anymore. Okay? So, what are the predictions, what are the results as far as the emission from isolated neutron stars are concerned, talking about the polarization properties of radiation? I will just review a few examples starting from magnetars, which are sources with a ultra strong magnetic field, 10 to the 14 or more. And let me just remind that the magnetar persistent emission is thought to come from the reprocessing of thermal emission emitted at the surface by resonant Compton scattering onto charges that flow in the magnetosphere along the closed field lines of a twisted magnetic field. Just a movie to show how a twisted magnetic field is. So it will start again. It starts from a dipole, and then it is not a time sequence. It just illustrates how the field changes if I increase the twist angle. Okay. Of course, this twisted field is a non-potential magnetic field, which implies that currents must be there, and these currents will flow along the closed field lines. The currents are, we think, made essentially of electron-positron pairs, but okay, that's a different story. Of course, I mean, we can guess what is the initial polarization of radiation selecting a models for the surface emission of the magnetar, although this is still far from being a settled issue. But there is also another point here that the scattering, the resonance scattering by the electrons circulating in the magnetosphere will change the polarization state of the photon. I just put it as an example the ratio, or better the relationship between the different scattering cross-section for OO mode and OX mode. And one actually can show that the polarization degree and the polarization angle depend on the twist angle, on the charge speed, and on the geometrical angles. This was a model discussed by Fernandez and Davis and our group a few years ago. So if I proceed, I can show you how the polarization angle and the linear polarization fraction changes in this model by changing the twist angle. And you see that while the spectrum changes, also the polarization angle and the polarization degree changes in an even more dramatic way by changing the twist angle. Okay, just a few words because Roberto Taverna, who is talking just after me, will concentrate on this about the polarization of radiation coming from bursts and flares, which are emitted from magnetar sources. Magnetar sources emit different types of bursts, from normal bursts to the hyper-energetic giant flares. The current state of the modeling is that the magnetar bursts and flares likely originate in a hot magnetically confined pair fireball, according to the original suggestion by Thomson and Duncan more than 20 years ago. So what we have done, Roberto will discuss this in detail, is to solve the radiative transfer for the two modes in the surface layers of the fireball. And the quite obvious prediction that one can extract is that because of the scattering depth for the O mode is much larger than that for the E mode, one expects that the intrinsic radiation from the fireball is highly polarized, although the spectrum is indeed BB, black body plus black body like. So here is a plot showing as a function of the two geometrical angles, the polarization fraction and the polarization angle for a typical intermediate flare like those emitted by 1900 during the burst forest. And you see that the polarization fraction, at least for a given combination of the two angles, is very large indeed. Okay, thermally emitting isolated neutron star will typically the X-ray dim isolated neutron stars. These are 7 close by sources with soft thermal spectrum with temperature of few tens of electron volts and periods in the range 3-12 seconds. Emission is thought to come from the entire star surface, which has an inhomogeneous surface distribution, which is dictated by the magnetic field. For the dipole, this goes like, T goes like the square root of cosine theta, where theta is the magnetic colatitude. We are not sure what is the radiation mechanism which is actually producing the radiation we observed in the X-ray range. As I said, it could be an atmosphere, it could be a condensed surface, perhaps with a very thin hydrogen atmosphere on top. Just to show you what comes out, I just report here the results for the phase average polarization fraction, according to calculation recently presented by Denis Gonzalez, Kanulev, and our group. This is the polarization fraction observed at infinity in the case in which the neutron star has an hydrogen atmosphere, fully ionized, magnetized hydrogen atmosphere. Please ignore this line here. I will discuss this later. Well, the colors here are perhaps not the, they are not the right ones, but anyway, and you see that in this case, you can have a very large polarization at infinity, at least for certain angles, but in the case of a condensed surface, the polarization is, well, not zero, but definitely lower, okay? So, I mean, the choice of, with all the other, keeping fixed all the other ingredients, the choice of the emission model is crucial to the polarization observables. So, very well, excellent. So, what about the future? As I mentioned at the beginning of my talk, there are a number of proposed missions. I listed here the 3 which I know better. There are other under study yet. The first one is called XP, Imaging X-ray Polarimetry Explorer, and it has already been selected as a NASA's next mission. Launch is expected late 2020. Then there is SHIPE, or XP as you would like. This is the X-ray Imaging Polarimetry Explorer. Not much fantasy in choosing the names for these missions, which is still competing for ESA M4. And if selected, the launch is expected, well, according to the original schedule, again late in 2020, but perhaps a bit later. And finally, there is a Chinese-led mission, which is called the XTP, Enhanced X-ray Timing and Polarimetry Mission, which is a strategic priority space science program of the Chinese Academy of Science, which is scheduled to fly within 2025. The 3 missions as use the same polarimeter, which is a gas pixel detector polarimeter, which has been developed by the group of Costa, Enrico Costa and Paolo Soffitta, Bellazzini et al. At INAF in Rome. The main difference between the three missions is in the size of the telescope, and of course XIPE should have the larger effective area and XPE the smaller. So this is a sketch on how the gas pixel detector works. Basically, it exploits the photoelectric effect and the fact that the photoelectric cross-section depends on the polarization state. Then you can reconstruct the photoelectron track, and from this reconstruction you can compute the polarization observables. So finally, what we will measure when the X-ray polarimeters hopefully will fly. Well, at least one will fly. Well, first let me say that phase result polarimetry can probe the resonant Compton scattering model for magnetars and pinpoint the source geometry and physical parameters, which is one thing, especially talking about the geometry, that spectroscopy alone cannot do. This is an example of a simulated observation with XIPE. The next figure will show the same for XPE. Of a bright magnetar persistent source, which is this one, the IXP1RXS J1708, and indeed you see that the fit, don't ignore please this, so these are the simulated data, the dashed line, the blue dashed line, ignore the red one, is the model from which data were generated, and the full blue line is the best fit. So indeed, if you make a simultaneous fit of the flux, of the linear polarization fraction and of the polarization angle as a function of the phase, these are integrated in the 2.8 or 2.6 maybe? 2.6 energy band, you can recover the model parameter and have a confirmation, if this will be the case, of the validity of the model, including the values of the angles, of the geometrical angles. Okay, this is the same for XPE, the same duration too. You see that the error bars are slightly larger because, of course, the detector has a less effective area. Second very important point is that X-ray polarimetry can univocally detect vacuum polarization, which is very important because this effect is still to be experimentally observed, although there are attempts in the lab to measure delta n. Let me say that X-ray polarimetry will not measure the difference in the refractive index. We just tell us that the refractive index are different. Okay, so I come back with the same picture as before. Pardon me, but this should be referred to XPE, not XIPE. That's Roberto's fault, which forgot to change the label on the figure. But the point is that if you generate the mock data according to the model, which includes QED, so with vacuum birefringence, then you get a nice fit. Of course, if you try to fit the same data with the model in which the QED effects are artificially turned off, then of course you get this. Okay, it's a warning that the time is up. Okay, I think okay, just a few seconds more. So, I mean, this will discriminate between the two different scenarios, QED on and QED off. Of course, we believe, of course, that QED is there, but this will tell us that effectively it is like that. Okay, this is again about the burst, but I can skip this because Roberto will talk much more extensively about this. So, thermally emitting neutron stars, this again I will skip. Just let me remind that thermally emitting the X-DINGs are not within the energy range explored by the current polarimetric missions, so it will be impossible to observe them with the scheduled missions, but there are soft X-ray polarimetry and polarimeters under study, and of course also in the case of X-ray dim isolating neutron star, it would be possible to discriminate between the QED and the no QED scenarios. according to the polarization fraction. And finally, just a few words about a very recent work we did about the optical emission for one of the 7, RxJ 1856. Quite surprisingly, this source has a large, or relatively large, polarization degree, which is larger than 16%, and it's completely anomalous with respect to the neighboring dim field stars. You see these control stars here. This is the source, this is Q, this is U. So we are pretty convinced that the determination of this polarization in the optical B band with VLT is robust. And if you take into account for the different models, and you also take into account that we know the pulsed fraction in the X-rays, which is very small, is 1.2%, you put everything together, the models without any QED accounted for works only marginally. But if you actually include the QED, then the models work quite well. So I'm not claiming that this is the first direct measure of the QED effect, but within the models we explored, I hope that George agrees with me, it is like that. So these models are compatible with the measure only if QED is there. Okay, I think I will stop here and leave just my conclusion up there. Thank you.
We have time for a few questions. George?
Yeah, first, does it work? Okay. First, sorry for this notice, one should never quote error with 3 digits.
Sorry, I didn't understand.
You quote the error of the polarization degree with 3 significant digits, which is not the right thing to do. But it's not important. But more generally, I would say that I don't think that any body of physicists has any doubts that the vacuum birefringence, vacuum polarization is there. So if you know how to include it correctly, it's even no point in investigating the case when there is no this QED effect. QED, it is well-established theory, and so on and so forth. So it is not quite scientific approach. But as I told you, nevertheless, of course, this measurement of polarization is very important by itself. And I would even say that we have no doubt that the magnetic polarization, vacuum polarization is there. But you can use this to sort of justify your models of the temperature distribution over the surface, which is in a sense much less certain than the presence of the QED effect.
No, I agree, and I think I stressed this in the talk, during the talk, on the fact that there is no doubt that vacuum birefringence is there. Still, it is actively searched experimentally in the lab by a few groups around Europe, mostly in France and in Italy, because there is no direct experimental evidence for it. And I think it is important because it should be quite important to test experimentally one of the prediction of QED, which we know holds. And this prediction is about the self-interaction of the electromagnetic field with itself. Because vacuum birefringence is precisely that. So the vacuum birefringence, in a sense, implies that the index of refraction is influenced by the electromagnetic field itself. So the speed at which light propagates depends on the electromagnetic field itself. So this is a different way of putting this. But I think that this is an important, it will make, of course, we have the theory, but it will show with beyond any doubt that in the strong QED limit, Maxwell equations are not all right. And of course, it's a bit like general relativity. When you go from Newtonian theory to GR, the equations are nonlinear. And the same is with the electromagnetic field.
I'm saying in relativity you have several ways, several options.
No. No, I was not making that point, George, of course. I was just saying that the equation describing correctly the electromagnetic field in the more general situation are not linear. Okay. As the more general equation describing the gravitational field. So Einstein's equation tells us that the gravitational field interacts with itself. And in this case, QED tells us that photons interact with themselves. This was the only point I would like to make.
Okay. Let us now...
Sorry. Yeah.
Interesting discussion, but we need to move on now to the next talk. This will be given by Roberto Taverna on the spectrum and polarization of magnetar flare emission.
Can you hear me? Yeah, okay. Perfect. So thanks, first of all, to the organizers for this opportunity. I will apologize for a couple of animations that will not work correctly, but I try to compensate with my words. So I divided the presentation in 4 parts. After a brief introduction about magnetars, I will discuss the theoretical framework of our model, also showing our numerical simulations and results. And in the conclusion section, I will discuss also some future prospects of the work related to the recent polarimetric missions under development. So magnetars are a particular kind of isolating neutron stars, observationally identified with soft gamma repeaters and anomalous X-ray pulsars that are powered by the strong internal magnetic fields. In fact, the X-ray luminosity exceeds the rotational energy loss rate E dot, that is of the order of 10 to the 32 per second for these objects. And their internal magnetic fields are expected to be higher than the quantum critical field, which is of the order of 10 to the 13 Gauss. But also the external fields that can be inferred from the spin periods and the spin down rates are quite strong and of the order, on average, of 10 to the 14 Gauss. In the soft X-ray band, spectra are well fitted by the superposition of 2 components that are blackbody plus power law for persistent magnetars and usually blackbody plus blackbody for transients. And an additional power law component at higher energies has been detected for several sources. But the most distinctive observational manifestation of magnetars is their bursting activity, which is divided into 3 kinds of different events classified according to their energy release. The giant flares are the most powerful, and they are composed by a strong high initial spike. A strong high initial spike with duration around 1 second, followed by a long pulsating tail. And the energy release, up to 10 to the 47 ergs, is essentially emitted all during the initial spike. But these events are quite rare. In fact, in the past, only 3 sources have been observed to emit a giant flare, while more frequent are intermediate flares and short bursts. The former are characterized by a duration up to 100 seconds, and they can also show pulsations, as in the case of giant flares. And short bursts have a duration smaller than 1 second and an energy release up to 10 to the 41 ergs. So all this phenomenology can be well explained within the twisted magnetosphere model. In fact, the internal field of magnetar is expected to be also highly wound up, and its toroidal component can exert a strong magnetic stress on the conductive surface that is normally balanced by the rigidity of the crust for normal neutron stars. But for magnetars with a strong internal fields, the stress can be strong enough to deform the crust and transfer the toroidal component of the field to the external magnetic field that becomes twisted. And the typical quantity that describes the twist is the twist angle delta phi. So giant flares and short bursts are related to these plastic deformations of the crust and to the magnetic reconnection of the field lines. Moreover, such an external field, as also Roberto says, is non-potential, and so charged particles must flow along the closed field lines, making the medium in which photons propagate optically thick for resonant cyclotron scattering that gives rise to the power law tails observed in the soft X-ray band. then photons are expected to be linearly polarized in the two normal modes in the presence of strong magnetic fields, with the photon electric field oscillating both either parallel or perpendicular to the KB plane. And we described also in this work the polarization in terms of the Stokes parameters, because they are additive quantities, and so in order to reconstruct the polarization properties of the radiation at infinity, one has only to sum together the single photon Stokes parameters once they are defined in the same reference frame. So, as I mentioned before, according to the model by Thomson and Duncan, magnetar flares originate in the sudden rearrangement of the external magnetic field that follows the crustal displacements that are triggered by the strong internal magnetic field. And this injects in the magnetosphere an Alfvén pulse that grow up more fast than in this slide. This Alfvén pulse dissipates into an electron-positron pair plasma that is magnetically confined within the closed field lines in the magnetosphere in a volume of typical radius R max, that is the distance at which the wave energy is equal to the magnetic energy. And so we describe the properties of the radiation in the presence of a steady trapped fireball, neglecting the contributions from relativistic outflows outside the fireball. And so we also the evolution of the fireball is not the aim of this paper, of this work, obviously. And we assume that the main source of opacity in this medium is due to magnetic scattering that we considered in the Thomson limit for the sake of simplicity, so as conservative and neglecting the electron recoil. But a complete version of the model based on the full Compton cross-sections is under development. But also, looking at the differential Thomson cross-sections, one can see that the opacity for extraordinary photons is strongly suppressed with respect to that of ordinary one by a factor b to the -2. And this means that extraordinary photons are expected to escape the fireball closer to the star surface, where, for example, the temperature is higher. And this will influence both polarization and spectral properties of burst radiation, as I will show. Obviously, besides scattering, there could be other second-order processes that becomes important in the fireball, such as thermal Bremsstrahlung, photon splitting, or double Compton scattering. One can see that the Bremsstrahlung between particles with the same charge is important only at very high particle energies and well outside the range we consider in our work. While electron-positron Bremsstrahlung is slightly enhanced with respect to the electron-ion channel, and it is negligible for photon energies above 1 keV and particle energies around 10 keV, which are the typical conditions for magnetar bursts. And so we neglected thermal Bremsstrahlung in our model. Instead, photon splitting in principle could be important in a wider energy range. And one can see that, assuming weak dispersive effects, the only allowed channel is the splitting of an extraordinary photon into two ordinary photons in the weak field limit. But in the non-relativistic regime, the cross-section for this process is much smaller than the Thomson cross-section. And in the strong field limit, one has also to consider an additional suppression factor. And so we can neglect safely also photon splitting, and it remains double Compton scattering as the main process responsible for photon production in the fireball. In particular, looking at the photon production rate Q, one can see that in the low energy range, photons tend to be distributed according to a Planckian, while for higher energy, scattering tends to establish a Bose-Einstein distribution. But as shown, for example, by Lyubarsky, the chemical potential is rather small, and so we can consider local thermal equilibrium in the fireball. In particular, we considered both the ordinary and extraordinary photons distributed according to black bodies at the base of the fireball. Actually, since the optical depth deep in the fireball is expected to be huge, we solve the radiative transfer only in a geometrically thin atmospheric layer of the fireball, characterized by an optical depth much greater than 1 at the base and much smaller than 1 at the top. And so we divided the fireball into a number of different patches. Sorry for the, oh, it works. Each labeled by the magnetic field strength at the patch center and the angle theta b between the star magnetic field and the patch normal z. We also assume that the patch dimensions are small enough with respect to the radial scale to neglect curvature, and so we can consider also plane parallel approximation. So, under these assumptions, the radiative transfer equations for the two modes assume this relatively simple form as functions of the infinitesimal Thomson depth d tau. But we found that solving for the Thomson, that could be a problem from a numerical point of view, due to the suppression factor I mentioned before that affects X-mode cross-sections. In fact, due to this, the propagation of photons in the fireball medium is different according to the polarization mode, with also different optical depth for ordinary and extraordinary photons. And in particular, the X-mode photosphere lies at different heights for different photon energies, while at the same time, the medium remains optically thick for ordinary photons at all the photon energies. So for this reason, we use the approach by Lyubarsky and solve the radiative transfer equations in terms of the Russell-Lamigne optical depth tau r for extraordinary photons that is related to their Russell-Lamigne cross-section sigma x. And we also use the suitable temperature distribution for particles that holds in the diffusion regime, but we verify that is also a good approximation at small tau. And using this distribution, one obtains this relation for tau r that differs from the Thomson depth only by a scale factor r, and also the ordinary and extraordinary optical depths are related to tau r by simple relations. So entering more in depth in our numerical simulations, we assume that at the base of each patch, tau r is equal to 1000, and it is equal to 0 at the top. And in order to reduce the computational time, we divided the fireball atmosphere into 3 different regions. In the deepest one, where both tau x and tau o are greater than 10, we did not integrate the transfer equations, assuming that both ordinary and extraordinary photons are distributed according to black bodies at the local temperature. In the intermediate region, where only tau x is smaller than 10, we only solve the X-mode transfer equation. Still, ordinary photons are black bodies at the local temperature. And in the surface layer, where both tau x and tau o are smaller than 10, we finally integrated the full differential equation system. Then the photon energy range is between 1 and 100 keV. The particle temperature distribution is that of before, with a bolometric temperature TB 10 keV. For the sake of simplicity, we assume that the magnetic field is dipolar, and with a polar intensity of the order of 10 to the 14 Gauss, and the limiting radius R max for the closed field lines that limit the fireball in the magnetosphere is twice the stellar radius, that is 10 kilometers. So we solved the radiative transfer equations using a simple lambda iteration method, and the output quantities of the code are the photon number intensities as functions of the optical depth, the photon energy, and the polar angles that the photon propagation direction k makes with either the stellar magnetic field B or the patch normal Z. And as an example of this latter case, these are the angular distributions of the photon number intensities for 2 different patches, characterized by theta B equal to 45 and 90 degrees respectively, and for a magnetic field strength 10 to the 14 Gauss. And you can see that, as expected from the scattering cross-sections, the ordinary photon intensity is much smaller than the extraordinary one, even if ordinary photons are somehow beamed along the direction of the stellar magnetic field. Then, since in our model the fireball is limited by the closed field lines, then all the patches in which its atmosphere is divided will be characterized only by theta B equal to 90 degrees. And so in this configuration, we calculated the emerging spectra from the patches. Here reported for 2 cases with B equal to 10 to the 13 and 10 to the 14 Gauss. And as you can see, the black solid line is the total intensity. The red and blue dashed lines are the X mode and O mode intensity. And essentially, the total intensity follows the X mode intensity, except for the smaller magnetic fields at the higher energies, where the difference between O mode and X mode distributions is smaller. And this is due to the fact that the suppression factor that appears in the X mode cross sections goes as the photon energy squared times B to the minus 2. Moreover, the X-mode intensity is flat at the lower energies, and this is due to the fact that X-mode photons escape the fireball at different heights closer to the star surface with different particle temperatures. So we sum together the contributions of all the patches in view in a ray tracing code in which the star is seen along the observer line of sight, and the viewing geometry can be controlled through the 2 angles of before, K and Xi, between the line of sight and the spin axis, and the magnetic axis and the spin axis of the star respectively. Then the point in view over the fireball surface can be determined through solving the terminator equation that gives this particularly complicated shape of the terminator of the surface that is also a function of the rotational phase. And so for these reasons, for the sake of simplicity, we neglected general relativistic effects in the code. We considered two emission models. Model A, in which radiation comes from the entire torus that limit the trapped fireball, and Model B, in which instead the emitting region is only a portion of this torus, but radiation coming from the planar slices that limit this emitting region is considered. Then QED effects and geometrical effects for polarization are accounted for, as in the talk by Roberto Turola of before, and we assume that the vacuum contribution to the dielectric tensor are dominant with respect to the plasma ones. And we can neglect vacuum resonance effects in our energy range because they become important only for energies lower than 1 keV. So these plots show the total X mode and O mode phase average spectra in the case of model A. And as you can see, as in the case of the single patches, the total spectrum is nearly superimposed to the X mode spectrum, while the O mode one is strongly suppressed. This also means that, according to our model, the burst radiation at infinity is expected to be highly polarized in the extraordinary mode, at least in the 130 keV energy range. Moreover, thank you, according to the spectral analysis by Israel et al. For the burst forest emitted by SGR 1900+14, we tried to feed the phase average spectra through a two black body function. These are the feed results, and the plots refer to the second row of this table. And the temperatures of the two components, as well as the ratio between the emission radii, are in broad agreement with observations. Now, our model is only an illustrative model and relies on a series of simplifications. And also, we did not explore the entire parameter space. Nevertheless, the model does not support the hypothesis by Israel et al. That the two components are related to the X mode and O mode photospheres. These other plots show the phase resolved spectra for model A and B and a particular viewing geometry with the corresponding pulse profiles, in order to show that our model is also able to reproduce the pulsations modulated at the spin frequency of the star that have been observed for the decay tails of magnetar flares. And this is possible not only limiting the emitting region in the case of model B, but also where radiation comes from the entire torus, provided that it is observed under a favorable viewing geometry. And then for the polarization observables, these plots showing the phase resolved polarization fraction as a function of the photon energy for both model A and B for two different viewing geometries confirm the high degree of polarization suggested by spectral analysis. In particular, the polarization fraction tends to decrease for photon energies above 50 keV, attaining a minimum of about 40%. And also, the polarization in the case of model B of the radiation coming from the planar slices, the limit emitting region, is in general more polarized than the photon coming from the torus, due to the fact that in the case of planar slices, one collects more photon coming from regions closer to the star surface where the magnetic field is stronger. And so X-mode photons are favored with respect to the O-mode ones. From the polarization angle as a function of the rotational phase, here plotted for 4 different viewing geometries, one can see that the dominating polarization mode is the extraordinary one, since the polarization angle oscillates around 90 degrees. And this is finally confirmed also in the phase average polarization observables plot for model A and B, plotted as functions of the viewing angles K and C, in which you can see the polarization degree phase average for model B is higher. So, as conclusions, we developed a theoretical model for explaining the spectral and polarization properties of magnetar burst emission, according to the original model proposed by Thomson and Duncan. Our model relies on a series of simplifications, as for example, magnetic Thomson scattering as the main source of opacity, and we also neglected the contribution from relativistic outflows. But the results of our model are compatible with observations, as, for example, in the case of spectral fits. And the model can also reproduce the pulse profiles observed for the decay tails of magnetar flares. Finally, the high degrees of polarizations expected will be easily accessible from the next generation X-ray polarimeters like XPE, XIPE, and EXTP. These plots show simulated measurement in the case of a real event studied by Israel et al. And as you can see, the simulated measurement recovered the model parameters within 1 sigma in all the 3 cases. And this means that indeed X-ray polarization measurement will be feasible in the next future. And this will provide proofs of the prediction given by our model. So thank you for your attention.
Questions? Yes, Matthew.
Those predictions are for the IXP and XIPE bands, but in other words, below 10 kV.
Yeah, 2.6
correct?
to 8
Right.
energy range, yes.
Even though lots of emission at higher energies gives you a different polarization signature, we don't
Yeah.
have something to sample that in the near future.
Now we have no models, no instruments, no model for the instruments working in the higher energy bands. But at least for these that work in the 2.6 to 10 kV energy range, the prediction is good. So for Yastrogam could be, yes, but yeah.
Thank you.
Do you expect any spectral feature in your
So we
cyclotron, vacuum, and so on?
We assume that the photon energy in our model is much smaller than the electron cyclotron energy, and so for the electron cyclotron feature or positron, we did not expect any because the energy range is between 1 and 100 keV, and our model is taken for a magnetic field that is tuned in such a way that we don't expect for these model parameters the cyclotron feature for electrons. Instead, for ions, the contribution is still more negligible because the energy, the cyclotron energy is even lower. So we don't expect for ions. For electrons, maybe considering higher energies and higher magnetic or lower magnetic fields, it could be.
Any other questions? Okay, let's move on to the next talk. This will be by Erbil Yügercinoğlu, and he'll talk on glitches as probes of neutron star internal structure and dynamics.
Hello everyone. Can you hear me? Okay. Hello everyone. I will talk about the potential usage of glitches as inferring the neutron star internal structure parameters. Oops. No, it doesn't work. Okay. Pulsar glitches are sudden increases in the rotation rate instantaneous to the precision of the data, which are followed by comparatively long recovery. As you can see, the parameter Q, healing parameter, quantifies the degree of relaxation of the glitch. And the glitch magnitudes are in the range 10 to the minus 5 to the 10 to the minus 12. And these are usually accompanied by a change in the spin down rate in the range 10 to the minus 1 to the 10 to the minus 4. Rapid spin up and comparatively long recovery says that there is a bulk sphere validity in neutron star because in normal matter interactions the large and sudden spin ups should be followed by sudden decreases. And in the literature, there are several works relating the glitch observations to the internal structure parameters. For example, Abney et al. considers the cross-core coupling, and Howitt et al. Argues the distribution of angular momentum within different physical layers, and Eason has considered the spin-up in neutral and charged superfluids. And also glitch observations are used for constraining the bulk properties of neutron star matter and equation of state. In this work, I will mention about how can glitch be used to infer magnetic field configuration and the temperature evolution. According to the standard glitch model, the vortex creep model, the cluster superfluid and the normal matter are coupled by vortex lines, thermally activated motion. At the time of the glitch, a very large number of vortices are released and impart their angular momentum to the crust. Due to this, the coupling between the superfluid and the crust is decreased, and superfluid decouples from the external torque. This is seen as a spin up or increase in the spin down rate, and recovery is seen as the superfluid recouples to the other parts of the star. In recent years, there is a theoretical challenge to this standard picture. Nicolas Chamel, by using band theory calculations, has shown that the drip superfluid neutrons from the crystal nuclei reduces the mobility of the superfluid, and it means that the angular momentum reservoir is decreased by a factor of entraining factor. Here is Mn is bare neutron mass, and M star n is the effective mass of neutrons. In the crust of neutron stars, M star is larger than Mn, so the angular momentum reservoir is somewhat reduced. So the way out is the involvement of core superfluid in the glitches. The glitch magnitude is related to the part that participates in the glitches, IS, the moment of inertia of the superfluid region that participates in glitches, and IC is the moment of inertia of the parts of the star which couples less than the glitch relaxation process, and delta omega s is the change in the superfluid angular velocity, and delta omega c is the rotation rate of the crust. In our recent works with the Ali Alpar, we have shown that the IS over IC ratio can be increased by superfluid decoupling from the external torque, by which vortices are not released from the core, but affected by the spin-up glitch in the crust. And also in the larger glitches, core superfluid can participate in some special circumstances. There are two configurations for flux tubes in the neutron star core, one with poloidal configuration, and the other is the toroidal field configuration. In main sequence stars, the staple magnetic field configuration is such that there is a toroidal field which is inside in a closed field region of the poloidal field lines. And as the surface magnetic field is increased, the toroidal field region's moment of inertia increases. In the case of poloidal field lines, the vortex line, poloidal flux line pinning is not released until they encounter. Vortex lines in the neutron star core are spontaneously magnetized due to direct proton supercurrents around them. They acquire 10 to the 15 Gauss magnetic field, and if vortex lines and flux tubes are both parallel to the rotation axis, they move without pinning. But in contrast, the toroidal arrangement of field lines, the vortex line flux tube pinning is inevitably realized. In our model, only the toroidal field region, which you see here, can participate in glitches. So This explains why the glitch magnitudes are small, because core moment of inertia is much larger than the grasp. So if all of the core participants, one cannot explain the glitch magnitudes. More importantly, our models predicts a exponential relaxation which is seen almost all glitches, after all glitches. It is given by toroidal moment of inertia. It's related to the toroidal moment of inertia, a relaxation time scale. The relaxation time scale depends on the spin down rate of the star, the core temperature, the radius of the location of the toroidal field region, the superfluid superconducting coupling parameters, for example, the proton fraction, and the proton effective mass, and the density, and the strength of the toroidal component. One prediction of our model is that as a pulsar ages, the relaxation time scale becomes very longer. So glitches resemble step-like changes without any significant relaxations, and this is supported by observations by Espinosa et al. And Yu et al. Well, usually glitch observations are fitted by a model with a linear recovery and an exponential recovery. Here you can see an exponential recovery term and our model prediction. Then if toroidal field's relaxation time scale is of the order of or similar to exponential decay time of observations, one can say that toroidal field's fractional moment of inertia of the toroidal field region is equal to the healing parameter. So one can infer the internal magnetic field configuration from glitch observations, which is inaccessible to the surface observations. And if the toroidal field relaxation time scale is much larger than the decay time scale of the observations, we can only have an upper limit. To date, there are 41 pulsars which displayed 76 glitches with exponential relaxation, and I applied my model to all of these glitches. For equation of state parameters, I have used 3 equation of state: Akmal et al., Akmal-Panderevanal equation of state, Latimer-Svesti equation of state, and Duchan-Ansel equations of state. I needed temperature evolution, for which I used Yakovlev et al.'s modified Urca process cooling and Aguilera et al.'s magnetic field Joule heating assisted field decay model. I have considered 3 places for the location of the toroidal field region, and the superfluid superconducting parameters are taken from Chamel and Bormand et al. I have also applied my model to the magnetars, but magnetar glitches have some peculiarities. First, magnetars do not have a stable spin down, and they show burst-like activities after all the glitches. So there is a strong evidence that magnetospheric processes play an important role along with the superfluid processes. They have anomalous Q values. They show over-relaxation, and from the characteristics of magnetars, due to the magnetic field decay, the magnetars have low spin down rates, which increases the relaxation time scale. And also magnetic field decay, magnetars have a very large persistent surface temperature. So magnetars behave different from radio pulsars, and their properties must be considered in detail with a physical explanation. Here are my results for magnetar glitches. Due to the Hall drift assisted field decay, in magnetars, the toroidal field component is about 1/100 of the poloidal field. So magnetars have lower toroidal field strength compared to their dipole field. And if a density of the core exceeds a certain density, certain critical value, direct Urca process operates, and magnetars high temperature, high surface temperature can be explained by a cooler core and a heater in a crust, as the Mesnagov, Yakovlev, and Kaminker et al. Have shown. And also the external torque and superfluid coupling, as our recent work shows, that there are extra terms in the Q values. Here are my results for the magnetar glitches. These are the observed time scales, and I have investigated the toroidal field regions relaxation cycle for two different cooling behaviors, one for modified Urca and second for direct Urca. In the case of direct Urca in the case of direct Urca process, I have obtained exact matches, and here are my conclusions. So pulsar glitch, post-glitch relaxation can be used to constrain the equation of state of neutron star matter, which is not done in the literature before. Also, pulsar glitch observations can be used to constrain the measure of the internal magnetic field configuration. According to my model, I can estimate the toroidal field region's strength and the moment of inertia. So the internal toroidal field of the core can be obtained within my model. Magnetar glitch observations are best explained by a core which direct Urca process operates. So pulsar glitch observations are an indirect and alternative view of a cooler core inside magnetars. Glitches with external torque variation implies a very strong coupling between the magnetospheric or accretion torques and the superfluid torques. And you can find details in my recently published paper in monthly notices. Thank you.
Questions? Jason?
May I ask you about magnetar glitches in magnetars? Yes. You said that direct Urca process may take place in magnetars. Yes. In that case, mass of magnetars should be more than averaged mass of other neutron stars. And is it confirmed by any observations?
Well, for the magnetar case, I used 1.8 solar mass, which is above the critical threshold for the Akmal-Pandey-Ravenel equation of state. And magnetar's magnetic field can be explained by a massive progenitor neutron star and also a massive neutron star in terms of the dynamo activation. So magnetar's strong magnetic fields can be explained by a strong magnetic fields can be explained by a massive neutron star motor from theoretical. And also Bhattacharya and Soni have a model which accounts for spin alignment of the proton-neutron interaction, which is the main cause of the magnetic field. So there is observational evidence. Also, there is an observational evidence that magnetars are found in a place with massive Meon-Sequus stars associations are present. So there are theoretical and observational clues that we can believe that magnetars are more massive than canonical radio pulsars.
So maybe you said this and I missed it, but so there are various observational evidences that neutron stars must have fairly stiff equations of state. Is that something that kind of naturally comes out of your glitch modeling as well? Would you, in absence of all of those other evidences, also predict that neutron stars must be fairly stiff?
Well, according to the time scale, I have found the equation of state parameters are density and proton effective mass and radius of the location of the toroidal field region. That does not guarantee that the equation of state is stiff or soft, but I believe that the equation of state should be stiffer. The best results are obtained in the case of Akmal-Pandaripanda Ravenel equation of state and the Duchamp-Ansel equation of state, which are both above, which both allow a neutron star mass above 2.01, and I have used here the maximum mass of the neutron star is 1.7 solar mass.
Okay, but it's something that doesn't come out of the glitch modeling directly, because you said in your summary that the glitches can place strong constraints on the equation of state. But
by using a particular model of the equation of state, you can constrain the, from the observed time scales, you can constrain the equation of state parameters and the location of the cross-core interface. So it helps to constrain whether the neutron star equation of state is stiff or soft. It can be done in principle.
okay, thanks.
Roberto.
Sorry. Just a comment and a question. So the comment is, I would say that the observational evidence that progenitors of magnetars are very massive main sequence stars, or started as very massive main sequence stars, is not that robust. Because the example was, the typical example is Westerlund 1, but that could have been evolved in a binary system.
Maybe.
And the question is, when you say that the toroidal magnetic field is less than 1/100th of the polaroid,
Maybe as low as 100.
this in the core anyway.
In the
right?
core, yes,
Okay.
in the core.
Thanks.
Yes.
You mentioned a very interesting paper by Nicolas Chamel, who showed that neutron superfluid density can be reduced about 10 times for some densities.
Yes.
This presumably happened because the pairing was not included when the band effects were calculated. And then there was a paper by Martin and Urban who showed that this can be avoided if it is taken into account that the size of superfluid gap is of the order of the forbidden zone between the bands. So what will change in your model if you leave this assumption that the band effects reduce the moment of inertia in the reservoir?
Well, the entrainment effect does not affect my relaxation time scale. Only it affects the moment of inertia fraction of which fraction of the toroidal field region participated in glitches. It doesn't affect the relaxation time scale. It is independent of the entrainment parameter.
So in other words, what will happen if you no more will need the core for the glitch?
There are two possibilities. If vortices in the core does not participate in glitches, they will still remain in the toroidal field region, and creep stops here due to the cross spin up. So superfluid decouples from the external torque, then the denominator decreases, IC decreases, but IS remains the same. And if in the core the vortices participate in the glitches, in that case IS increases. So increases, yes.
Will you you still have such a nice match to the observables as you showed on some slide?
I have searched for the Q values are published in the Yu et al. And the Espinosa et al. Papers. I compare with them so to determine the ITOR. I only applied my model to the constrain the entrainment parameter in my paper
Oh, that was very
2014 to only the Vela glitches, and I obtained average of 4.4 for the M star over M.
I see. Okay, thank you.
I think we can break for, oh, okay. One more question, last question.
Thank you. Did you include hyperons in any of these models of the equation of state which you used?
Well, the toroidal field region remains close to the equator and bounded with the outer core region, so hyperons do not exist at these densities.
But I'm asking this because if you need a direct Urca process, also direct Urca-like processes can operate with hyperons involved, and some of them don't have a large threshold. So,
The pulsars with show glitches are older than 10 to the 3 years old, so the cooling wave from the center has already reached to the cross-core base. So you don't have to consider hyperons. It affects only the mass and the density, like
you
parameters.
have additional neutrino emission from the process on hyperons. You can have this. Yeah,
Yes,
so
it decreases the temperature, so the relaxation time scale gets smaller. Its effect will be like this.
but
the relaxation
you told
times-
That you, I'm sorry. You told that you need direct Urca processes to describe the data properly, right?
Yes, because it is proportional to temperature.
Yes, but I guess what he's trying to say is a hyperon
Also,
presence
hyperon
could be an alternative to direct Urca
Yes,
to
of
provide
course,
low
of course.
temperatures.
This is all, I solved only a way of out.
Yeah, and maybe you don't need a direct Urca on protons, but just on lambdas.
But in
With
that
protons
case,
involved,
the
but just
radius gets smaller, and if radius gets smaller, my relaxation time scales gets bigger.
But this is a quantitative say.
Yes. So the quantitative details, maybe the two of you can discuss in
Sure,
the coffee
thank
break.
you.
Let's thank all of the speakers in the session again.
Раз, 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 два, три, четыре.
Okay, so welcome to the second part of the afternoon session. It's time to start. And the first speaker is Francesco Cotizzelati. We will talk about the systematic study of magnetar outbursts.
Okay, thanks. So I will present the results of the first systematic study of all magnetar outbursts observed in the past 20 years in a project that I started at the beginning of my PhD about 3 years ago in collaboration with my supervisors, Nanda Rea and Sergio Campana, as well as José Pons from the University of Alicante and Paolo Esposito from the Anton Pannekoek Institute of the University of Amsterdam. So first of all, I would like to give you a brief introduction, an overview on the observational properties of magnetars. So they are about 25 isolated X-ray pulsars, according to the McGill online magnetar catalog, whose X-ray luminosity is typically in the range from 10 to the 33 to 10 to the 36 erg per second, which is generally larger than the rotational energy loss rate for these sources. And for this reason, the emission from these objects is thought to be ultimately powered by the decay and the instability of their huge magnetic field, up to 10 to the 14, 10 to the 15 Gauss at the surface, rather than by the rotation of the magnetic field. They are observed to emit over a broad range in the X-rays, from the soft X-rays up to hundreds of keV, and their spectrum can be typically described by a thermal component, which is usually modeled by a black body, plus a non-thermal component, power law-like component, extending up to hundreds of keV. They all rotate with periods between 2 and 12 seconds, and the dipolar component of the external magnetic field is estimated to be, from the rotational properties and in particular the spin down rates of these objects, of the order of 10 to the 13, 10 to the 15 Gauss, which actually makes these objects the most magnetic sources in the universe. The hallmark of magnetars is their flaring activity, peaking especially in the hard X-rays and in the soft gamma rays, encompassing a broad range of time scales from a few milliseconds up to hundreds of seconds, and luminosities, reaching peak luminosities from 10 to the 39 to 10 to the 47 erg per second for the most powerful events. They all show a faint counterpart in the infrared and optical bands, and in 4 cases, pulsed radio emission was observed, although only during outbursts. So, as I mentioned before, the hallmark of magnetars is their flaring activity. Actually, Roberto Taverna was showing a similar slide 1 hour ago. We can roughly classify these bursts in 3 categories according to their duration and spectral characteristics. So we have the short bursts lasting from few milliseconds up to seconds, showing peak luminosity from 10 to the 39 up to 10 to the 31 erg per second, with a typical thermal-like spectrum, usually described by a black body with temperature from 30 to 40 keV. Then we have the intermediate bursts lasting from 1 to 40 seconds with larger peak luminosities compared to the short bursts up to 10 to the 33 erg per second. The morphology of the light curves is really diverse from burst to burst, but they are all typically characterized by an abrupt onset which is then followed by a slower decay. And again, their spectra is black body-like. Then we have the more rare giant flares. Actually, we observed only 3 events in the past 40 years, where the X-ray luminosity exceeds 10 to the 34 erg per second, up to 10 to the 37 erg per second, and they are characterized by this initial hard X-ray spike, followed by a decaying curve, which is modulated at the spin period of the neutron star. Besides bursts and flares, magnetars exhibit powerful outbursts. So during these events, the persistent X-ray flux increases on time scales that are not well constrained by the observations, but they are thought to be from hours to days. The X-ray flux increases by a typical factor ranging from 10 to 1,000, and then declines, recovering the quiescent level on a much longer temporal time scale, ranging from months to years. Two main mechanisms were proposed in the past decade to explain the outburst activity of magnetars, one invoking an internal source of heat, and another one invoking an external source of heat. According to the former mechanism, the outburst activity of magnetar is triggered by magnetic stresses in localized regions of the neutron star crust that are able to deform part of this crust in a plastic way. The plastic flows then convert mechanically the magnetic energy into heat, and part of this heat is then conducted up to the surface layers of the neutron star and radiated in the form of the observed thermal afterglow emission. But in addition to this, the crustal displacements implant a strong twist of the magnetic field lines outside in the magnetosphere, probably localized in a restricted region of the magnetosphere, and it is then thought that the outburst evolution is regulated by the resistive untwisting of this bundle. Both mechanisms are likely at work in magnetar outbursts, and actually the timescales involved should be of the order of a few years, which is actually observed in the data. During my PhD, we carried out the first systematic and homogeneous analysis of the spectral properties of magnetars in outbursts, actually with two main goals. So the first one was to model all the cooling curves for these episodes in a consistent way, especially considering that all these events were studied only individually by separate teams, also having different assumptions, for example, on the adopted models, such mainly the photoelectric absorption model, as well as the models describing the continuum emission. On the other hand, given the larger sample of magnetars outbursts analyzed, we were able to search and investigate for possible correlations and anti-correlations between different parameters, such as the outburst energetics, the quiescent luminosity, the flux enhancement, the magnetic field, and the characteristic age. In a future work, we will use the results of this study to gain deeper insight into the emission processes, especially via modeling with state-of-the-art internal crustal cooling codes. Here below, in particular, I show two examples where actually the cooling curves of outbursts can be described, in many cases, either by fixing the quiescent luminosity and varying the injected energy inside the crust, or, as you see on the right, by fixing the amount of injected energy in the crust and varying the quiescent luminosity. Now, to give you an idea of the numbers involved in this project, we analyzed a total of 23 outbursts that were observed from 14 different magnetars, plus 2 rotation power pulsars, namely PSR 1119 and PSR 1846, which experienced actually magnetar-like activity in the past decade, plus the peculiar central compact objects at the geometrical center of the supernova remnant RCWV 103, which actually underwent a couple of outbursts in the last 18 years, but Andrea De Luca will talk about this in more detail in the next days. So the total data analyzed sum up to about 1,100 X-ray observations acquired by different instruments on board satellites such as ROS-60E, BeppoSAX, Chandra, Swift, and XMM Newton, for a total of about 12 megaseconds of data acquired between 1998 and basically a couple of months ago. So the basic steps for the data analysis included the reduction of the raw data sets and the extraction of spectra for all these observations. Unfortunately, we were not able to perform this study in an automatic way, but we had to consider all these observations individually, owing to, for example, pile-up effects or sources lying on bad pixels and hot columns, or of the detector of the instruments, or also we had to correct for possible scattering halos or diffuse emissions, such as pulsar wind nebulae, or contaminating sources in the surrounding of our targets of interest. Then we adopted the canonical models to describe the emission for all these sources, in particular single black bodies, or in most cases the superposition of more than one black body, a black body plus a power law, but also we tested more physically motivated models, in particular accounting for the resonant Compton upscattering of thermal photons from the surface onto the charged particles in the external magnetic field of these neutron stars. This in turn allowed us to extract all the fluxes and luminosities for all these sources, including both absorbed and unabsorbed fluxes, luminosities for the single components and the total luminosity, as well the bolometric luminosity from the extrapolation of the models adopted for the X-ray emission. Then we extracted all the light curves and we modeled empirically, especially the bolometric cooling curves, to gauge the total energy released in these events and especially the decay time scale. Actually, all these cooling curves were modeled in a consistent way with one or more exponential functions. So the decay time scale refers to the e-folding time of these exponential functions. Here you see some examples of high-quality X-ray spectra for different magnetars acquired mainly by Chandra and XMM Newton. Here I also highlight the contribution of the different components to the observed X-ray emission. You see that in most cases, more than one component is needed to describe the overall X-ray emission, but in other cases, such as SGR 1833 and SWIFT 1834, a single black body model alone was enough to describe the overall emission. Here is an example of a cooling curve. So this is one of the 23 examples of the cooling curves we actually extracted from one of the most famous magnetars, 60AJ1810, that underwent a powerful outburst in 2003. And here you can see the evolution of the absorbed X-ray flux, of the X-ray luminosity for both the thermal components adopted to describe the emission, as well as the X-ray luminosity. On the right instead, you can see the decay, the time evolution of the bolometric luminosity with superimposed with the black line, solid line, the best fitting double exponential model to describe the decay. So here in particular, in the top panel, you can see all the fitted models to our sample of magnetars. Here, the flat part of the models are mainly extrapolations of the models towards the outburst onset, which we define as the epoch of the first burst detected from these objects. And this is actually a conservative assumption because we don't really know if the X-ray flux at the outburst onset is really similar to those observed, for example, 10 days after the onset. This is the model that we adopted to fit all these cooling curves, so one or more exponential functions, plus a constant term accounting for the quiescent level of these objects. Actually, also searches in archival data were carried out to unveil the real historical minimum flux for these sources. And then all these cooling curves were integrated from the epoch of the outburst and set up to the epoch of the recovery of the quiescent state to estimate the energy released. Here in this table, I show actually all our results for the decay time scales, both for the bolometric luminosities, but also for that of the single components, whereas on the last column in the right, you see values for the energy released, which typically range from a few 10 to the 30 ergs up to a few 10 to the 33 ergs for the most powerful events. Given all these results, we were then able to perform correlations and anti-correlations between different parameters. So here is a plot summarizing the results of this search. And the statistical significance for a correlation was evaluated either with both the Spearman-Rank correlation test and the Kendall-Tau test. And you can see that actually we can find different statistical significant correlations among different parameters. And I'm going to show you some of these results in the next slides. Also, the shape of the correlation was investigated via a power law regression test. And here I report also the rough values for the power law index derived between the correlation, derived for the correlations between these parameters. So now I want to discuss a bit some of the most interesting results we obtained. So here in particular on the top panel, you see the maximum luminosity increase observed during the outburst as a function of the quiescent X-ray luminosity, whereas in the bottom you see the total outburst energy released in the event as a function of the maximum X-ray luminosity. Here I also show the value for the statistical significance according to the Spearman test. And what actually you observe here is that large flux enhancements can only be observed in faint quiescent magnetars. That is this case for the magnetar SGR 04818, whereas the persistently bright source were never observed to undergo powerful events. And this actually means that the definition of transient magnetars as opposed to persistent magnetars is actually spurious because it only reflects the different quiescent luminosity. On the other end, you see that the crustal cooling codes are able actually to describe all these properties. In particular here, you see that for a fixed injected energy, the lower the quiescent luminosity, the larger the observed flux enhancement, and on the other end, the larger the quiescent luminosity, the lower the flux enhancement. A more physical interpretation of these results will be the subject of a future study. Other important correlations here are the quiescent bolometric thermal luminosity as a function of the external dipolar magnetic field. Here the correlation is significant at the level of 3.3 sigma. In this plot I also included, besides the magnetars, also the central compact objects in gray, the rotation powered pulsars for which a clear thermal emission was detected in red, plus the X-ray dim isolated neutron star in orange. You see anyway that the central compact objects depart a bit from the general observed trend, and this is expected considering the hidden magnetic field scenario proposed to explain the low external magnetic field of these objects, according to which actually in the first stages of the neutron star life, a magnetic field of a few 10 to the 12 Gauss can be buried into the inner crust by fallback accretion of the material of the supernova debris onto the neutron star. And in this way, the external magnetic field is lower than the internal hidden magnetic field, and so does not trace the bolometric luminosity. According to this scenario, the magnetic field should re-emerge on a time scale ranging from 1 to 100 kiloyears, and so if we are patient enough, we should see the central compact object to shift on the right side in this plot. Below, you see the same plot where central compact objects were removed. The correlation is higher, statistically higher in this case, but again you see that the rotation power pulsar seems to depart a bit from the observed trend, and actually this could be explained in terms of continuous bombarding particles onto the neutron star surface, providing an additional source of heat beside those coming from the interior of the neutron star. Other correlation, here I will be pretty fast, the energy released versus the dipolar magnetic field. Here a correlation is evident, and it is in broad agreement with the idea that magnetar outbursts are ultimately powered by the dissipation of the magnetic field, whereas below you see the outburst energy as a function of the characteristic age. Powerful events will be observed only for relatively young objects, whereas no powerful events will be observed according to this plot from relatively old magnetars, such as, for example, the X-ray dim isolated neutron stars. Last correlation I want to show you is the decay time scale of the outburst as a function of the outburst energy. again, a clear correlation is evident, and it is actually telling us that we observe a similar decay pattern for all these events. We never observe very powerful events returning to the quiescent level in a short time scale, or we never see very weak events that actually take a lot of time to recover the quiescent level. This is expected both in the interior crustal cooling model, because the outburst is expected to be more energetic if the energy is released deeper in the crust. And if the energy is released deeper in the crust, it will take much more time to diffuse up to the surface layers. Such a correlation is also expected in the untwisting bundle model with a specific relationship between the decay timescale and the energy, which is actually observed in our data. I just want to end my presentation showing that starting from a couple of days ago, all the results of the study were made publicly available on this website. Here you can see the link. Feel free to surf starting from now, with different sections available. What you see here is, for example, the possibility to plot different parameters versus other parameters. I also uploaded the right ascension and declination. So in principle, if you believe in a correlation between the declination and the magnetic field, you can test it. Here is especially the plot I showed before as the quiescent luminosity as a function of the magnetic field. And what is important here is that actually you can create your favorite function and fit it to different combination of parameters. So if you expect, according to your models, a specific correlation, actually you can test it against the data. And finally, also all the spectral files, response matrices, and auxiliary files are again available. So choose your favorite observation. You can extract all the relative data, redo the analysis, possibly find mistake in my analysis, and also re-estimate fluxes and luminosities. That's it. Thanks.
Are there questions, comments? Jez.
Obviously, really nice resource for the community. I was wondering about this one correlation that you were showing between burst energy and characteristic age. So how many orders of magnitude does that cover, and what would happen if you were to extrapolate that all the way down to a few tens of years or so?
Well, I did not
characteristic age, not the decay timescale. But
this one.
yeah, I couldn't quite see that. Okay, so it covers a few orders of magnitude already. Yeah. Okay.
So you mean if I extrapolate to
Down to very young, basically newborn magnetars.
Yes, yes, in principle I could expect even more powerful events. Actually, it's something we can predict according to our modeling of the shape of the correlation between these objects. And yes, so it's something predictable, but I don't know, I'm not able right now to estimate. Should be something like 10 to the 43 or 10 to the 44 error per second, maybe.
Are there other questions? Comments? Let me just ask a question. I thought that the characteristic age of 0418 was larger, right?
Well,
this looks like the true age.
Well, this is derived the characteristic age under the classical formula P over 2P dot, and actually I computed it using the most updated timing solution from this object.
It's kiloyears. Okay.
Yes, sorry.
This explains everything. Okay, so thanks again, and let's move to the next speaker. So it's time for Matthew Baring to give his talk.
We're still not there. It should be good. Okay? And laser pointer. Okay, we're good. So thanks again to Roberto. Okay, so what I'm going to be talking about is a project that was started during my former PhD student Zorawar Wadia Singh's PhD thesis. He's now a postdoc. Together with Pete Gonthier and Alice Harding, we've moved it along, and we're almost at the conclusion of a stage, which we're going to submit a paper in the next couple of months. We're just polishing now. So these are the results from that paper. It's modeling quiescent emission of hard X-ray tails, discovered 13 years ago in magnetars. Okay, so we now all know what magnetars are. Lots of good talks today summarizing their general properties. Here they are on the PP dot diagram, up here in the red squares, with magnetic fields typically above 10 to the 13 Gauss, ranging up to 10 to the 15 Gauss. Okay, so hard X-ray tails, magnetars were known in quiescent emission in the thermal X-rays, and then we were able to, with Chandra and XMM, see steep X-ray tails to them. And then the discovery led by Wim Hansen and Lucian Kuiper and Peter den Hartog later, and others have been found these hard X-ray tails in a total now of 9 magnetars. So they're very, very flat in the new representation. Here is the energy. They extend above 10 keV all the way up to about 150 keV. Then we don't have sensitive actual detections, but we do have upper limits from COMPTEL. And so that's years ago. These were discovered in RXT data and integral data, and we know now that there must be some turnover here. We don't know what produces it, but it has to be there, and eventually we'll be getting to modeling that. Right now we need added sensitivity in this band in order to be able to really do good spectroscopy. What we also see is that the pulse profiles vary as you go through energy band. If you go from low energies all the way to high energies up here in the RXT, you find that you get a very much different profile, much broader and less structured profile than you do down in the thermal X-rays from the surface. Okay, here's another blow-up. Same thing. Here we are for RxJ 1708, thermal, power law, steep power law tail, RCS type emission, and then we have these very flat spectra, typically e to the -1, that must turn over. Okay, they're common. There are 7 of them where we have detections from Enoto's Teru's paper. The thermal, if you look at that in this new representation, same deal, you find that lots and lots of the power in X-rays appears in the hard X-ray tail. So it's non-thermal emission. If you compare it with the Crab pulsar, with Vela up here, and 1509 coming down here, you find that the spectra do this. So they're very, very flat, but they don't extend. And so they are very different from highly magnetized pulsars. Here's some of the data on the actual spectral indices for the 9. And the hard spectrum is typically somewhere between a 1.7 index, 1.1, 1.3, 3, 0.7, 0.93, 0.8. So you can see there's a range of the spectral indices. Those are in the unpulsed spectral indices, which is mostly what we measure. So the idea that came out a few years after the discovery of the tails was that resonant Compton upscattering was a way to get this. Okay? It's a hard thing to avoid, actually, because the systems, while they're optically thin, as long as you have energetic particles around, it's very, very efficient because it's resonant to the cyclotron frequency, the actual scattering cross-section. I'll show you that shortly. So a number of groups have been involved in this. And so what you do is you use the hard X-ray, you get the non-thermal hard X-rays purely by a magnetic inverse Compton scattering of the surface thermal X-rays. You've got a big bath of thermal surface X-rays, and you get, just as long as you have relativistic electrons lying around and they're energized by some activation mechanism, they will be heated by inverse Compton scattering up to very hard X-rays and into gamma rays as well. So you could do this by a conventional pulsar electrodynamic potential type model, but that's not actually the preferred model. It's really the large-scale currents associated with twists in the magnetic field, with magnetars associated with the closed field line regions or maybe neighboring boundary quasi-open field line regions. But let's think about the closed field line regions in the equatorial regions. The currents and charge densities along these field lines have to be far in excess of the Goldreich-Julian values. That just comes about because you're talking about 10 to the 35 ergs per second in hard X-ray tail luminosity. So the putative locale of scattering is 1 to 10 stellar radii from the surface, above the surface. Okay, physics, resonant Thompson cross-section. So if you're looking at Thompson scattering as we know it from electrodynamics, we have a flat cross-section, just like that, as a function of energy, log scale, in units of the cyclotron frequency. Okay? At the cyclotron frequency, classical electrodynamics, as evinced in the paper by Canuto and al., shows that you have a resonance that comes directly out of the dispersion and the fact that electrons in a magnetic field get stirred up by an incoming photon. And they get the resonance, and both the modes, the polarization modes that Roberto Girola talked about, are highly resonant here, and they have roughly the same cross-section, but not exactly. They do if both the photons are propagating along the magnetic field, and the preferred state of propagation is circular polarization. However, there's this wide disparity between modes if you're in the low frequency regime, and that's what's been discussed in a couple of talks so far this afternoon. Okay? What we are looking at in this situation is we're actually looking at where the two photons are propagating parallel to the magnetic field, which means theta equals 0, and therefore the cross-sections are essentially identical. And they're resonant here. We have to cap those resonances. You can't, in a classical sense, you don't cap them. It's divergent. So you have to introduce something that's a little bit exceptional, which is quantum mechanics. And in fact, to get it right in strong fields, you actually have to introduce quantum mechanics too, because for this particular problem, we're dealing with ultra-relativistic electrons and photons coming up. So the photons now have a finite energy. They're not very low in the rest frame of the electron. They're actually quite significant. So the cross-section without a magnetic field would be this green line, which is the familiar Klein-Nishina cross-section. It's diving off. This is for a field in units of the quantum critical field, 4 times 10 to the 13 Gauss, and that's 0.1. So that's 4 times 10 to the 12 Gauss. As you increase and get to magnetar fields, you find that not only do you get Klein-Nishina reductions denoted by, if you like, these purple dots or the black curve, you still get the resonance, but the resonance drops relative to the Thomson value of the cross-section. And you get distortions to the shape, and you have to cap the resonance with the finite lifetime of the intermediate state of the electron. So that's the physics. We put this all into our calculations to get the spectra that I'm going to show you. Okay. There is an element to this we did first, and that was what happens to the particles. That's the cooling. And right now, you have to do the cooling, you have to do the spectral production, which is what I'm talking about today, and then you have to put the two together. We're yet to put the two together. So we did the cooling a few years back, and what you've got is, so you've got these X-rays coming off, and at some interaction point for your upscattering, you have a cone of soft X-rays. It's collimated, it's highly collimated, and it's about the radial direction. Okay, but the magnetic field direction is inclined to that, so the ability to sample kinematics that might set up a resonant interaction, and that resonance is at the cyclotron frequency in the electron rest frame, that depends on where you are on a given magnetic field loop. Low altitudes, you have a high magnetic field. High altitudes, you have a low magnetic field. So if you just take the surface emission, we plotted these general plots of a cooling rate, which is the resonant Compton scattering cooling rate, gamma dot, to the electron Lorentz factor in units of seconds to the -1. And a dynamical crossing time at the surface is C over the neutron star radius, so 1 over T escape, if you like, is that line there. It's 10 to the 4 to seconds to the -1. And all the curves that you get for different field strengths, 10 to the 2 times B critical, 10, B critical, 0.1, etc., they all have this type of behavior, this morphology. In this regime, it's non-resonant. You're not actually ever accessing the resonance because the Lorentz factor is too low. In this regime, you're getting an inverse image of the Planck spectrum of the surface thermal photons. And that's sort of reversed and by the kinematics of the resonant Compton scattering interaction. And then you eventually get into a power law tail. So if you inject particles at low altitudes where they sample high magnetic fields, if they have a Lorentz factor of, say, 10 to the 5, they may hit, for B equals 10 at the surface, they hit this resonance orders of magnitude in cooling rate above the dynamical scale. So they cool rapidly. They go boom like this down to a field that's lower. They continue to cool because the field is still sufficient in order to be able to access the resonant cooling. Then eventually you get to the maximum altitude, the magnetic field stops, and then the particles go around to higher field strengths, but they're now below the resonance, so they're non-resonant. So they don't actually cool, so they stop. That's really what's going to happen. Okay, So now let's look at the spectral production. We're not going to do the actual cooling. What we're doing is developing templates for spectra that you produce and seeing what the general character and how it relates to the neutron star geometry, the magnetar geometry. So here we have a plot of resonant interaction geometry. Okay? Maybe I'll focus on this one here because it's closer to this legend. Okay, so here's your neutron star. And your magnetic field's a little faint loops here. It's a little hard to see, but they're your magnetic field loops. And we've just got linear scales in 2 dimensions. With this plane is going to contain the plane of the direction of the line of sight to an observer. So if you'd like to tip the plane around like this, the line of sight to you, the observer. That's how we're viewing it. The viewing angle, the observer is this little eye here. So that's you looking down to the neutron star, and we've got all the magnetic field lines in that plane, and then we've got these contours. These contours are contours of the final upscattered photon energy as a function of position, okay? So what happens is you want to have a resonant interaction, which depends on the initial photon energy, and which is a soft thermal surface X-ray, and the angle of that photon as it comes off the surface makes with the local magnetic field wherever it interacts and scatters. But also, your final photon energy depends on being close to the resonance as well. So there is a direct correlation between final photon energy, which is color-coded from about 10 to the 3 in units of MEC squared down to 10 to the minus 4 in units of MEC squared. So this is gamma rays, this is around the thermal energies, and this is down in UV. These curves, you have pairs of them. One of them sits here, say here's one for 1.6 keV. Here's another one for 1.6 keV. And they're separated, they're pairs. These are curves that indicate resonant interaction locales that produce an energy of 1.6 keV. As you go up in energy, the positions of the resonant interactions converge, and they coalesce eventually near this blue line here. And this blue line here is where you're getting all your gamma rays. But otherwise, you're getting 16 keV. The black line is 160 keV. And so most of your X-ray emission that you would get from this model would appear in these regions here, would come from these regions, okay? But they produce, when you look at it, like you look at the radial, you look at the normal to these curves, these contours, it's not necessarily directed. It's directed up this way. It's not directed towards an observer. So the observer doesn't necessarily see that. Some observer would, but you as an observer would not necessarily see that. So what happens is, if you look at 3-dimensional orthographic projections, you pick a particular viewing angle, which is a function of pulse phase. So if you've got a viewing angle, let's say here, let's say 30 degrees, and that will depend on your phase because that's an instantaneous viewing angle with respect to the magnetic field axis, but the magnetic field is spinning, tracing a cone in space. So you will actually cycle through a sequence of these back and forth as you go through pulse phase. And what you see is it's color-coded with the same color coding, and you see this is the magnetosphere that you see at a particular energy. And what you see is that the black and blue stuff, which is the hard X-rays that are beyond 160 keV and into gamma rays, comes from a very small portion of the magnetosphere. Mostly what you see is red and yellow, and that's soft stuff. That is stuff that is below 150 keV, even well below that, below 10 keV typically. And that is dwarfed by the surface thermal emission. So the magnetosphere is largely producing soft emission. Okay, so now we get to the spectroscopy. Okay, so let's focus on the left first. What we've plotted here is a differential distribution, a straight differential distribution. It's not multiplied by E squared. Here's the energy, here's an MEV up here, and here's a KEV down here. Okay, so the spectra have this really weird sort of stuff going on. They have 2 spikes, a quasi-power law in between, and rapid drops here. So you think you've got a resonant cross-section that is entirely resonant, and then you're shifting it left and right in frequency space. Okay? How you shift it depends on the kinematics. The kinematics have 2 elements to it. One is the incoming photon, which is a soft energy, a soft photon of energy in X-rays, which means this is about 10 to the minus, these are scaled in terms of MEC squared, so it's about 10 to the minus 3. It also depends on the angle of the photon with the soft X-ray with respect to the local magnetic field at the point it has a resonant interaction. Okay, so that's one ingredient, and that determines those previous geometric curves that I've talked about. That has to be approximately equal to the B in dimensionless units. But also, in order to, you have your final photon angle and final photon energy, and they're correlated. So if you change your angle with respect to the local magnetic field, which is your viewing angle, your observer viewing angle, instantaneous as a function of pulse phase, then your final photon energy is also couples to this directly. So you see the spectrum changing. Since your instantaneous viewing angle is a function of pulse phase, you expect your final photon energy is also strongly a function of pulse phase. What's plotted here are two cases where you look at the spectra, you get the power laws. This power law is roughly e to the plus 1/3. Okay, that's very flat. It's taken for a case where we're not actually looking down a magnetic field plane, but we're inclined by 5 degrees to it. Okay? Here it's we're orthogonal to it. So instead of the magnetic field plane being like this for you, it's like this. So it's 90 degrees. What you see is when it's like this, the kinematics inhibits Doppler boosting. When it's 5 degrees, you get a fair amount of Doppler boosting, which pushes the spectrum up above 1 MeV. If you take 0 degrees, I'm not going to show that, it comes up here. You get very strong Doppler boosting. Classic kinematics associated with inverse Compton scattering. You back off it a bit, and what you find is, so you get these flat spectra with the cusps, and the cusps are images of the resonant Compton cross-section, the full Compton cross-section. I've also shown data here. Okay? These are all done for different Lorentz factors. Low Lorentz factor, 10, 30, 100, 200, 300. And you sort of see that there are some resonant regimes and there are also non-resonant regimes sitting there. It's all very complicated. And we want, in general, you're going to get a superposition of this type character. If you go to this orthogonal case, your kinematics for your final photons are very different because this angle looks fairly close to 0, so this term tends to disappear. And what it does is it tends to reverse, that you find the hardest spectra come from the lowest Lorentz factor electrons, which basically means the electrons are moving somewhat away from you and you're seeing backscattered photons. Okay? It contrasts the 0 degree case that I'm not going to show, where all these line up in a sequence of the highest Lorentz factor gives you the hardest spectrum. Okay, so some convolution of all this sort of character will appear in the overall spectrum. Okay, we're going to show you one convolution in a couple of slides. Let's first highlight, okay, so now here's another case. Here we're doing now, instead of a variation with Lorentz factor, we're doing a variation with viewing angle. It's instantaneous viewing angle. So as a function of pulse phase, we oscillate sinusoidally between values of these. Okay, so sometimes you're very close to the magnetic pole, sometimes you're very, 180 degrees away in phase, pulse phase, you're well away from it. And you see that you get flat spectra, sort of flat spectra, really flat spectra, but now you get this large suppression of the actual flux. There's 5, 3, 1. So you've got about 4 orders of magnitude in flux. Okay? A little bit of a change in the maximum photon energy. So you sort of see it, you're going to see the spectrum are going to flap around if they're allowed to be just inverse Compton scattering. Okay? However, they're not going to be. Because we're right down close to the surface, we're at 4 times R max represents the maximum altitude of the field loop in units of the neutron star radius, so it's 4. So that's not very high. The magnetic field is always, it's 100 here. The polar magnetic field is 100, so it's 4, that's 50 divided by 4 cubed is what that field is. So it's just about below 1, in other words, the critical field, at the maximum extent. Here we show some data from 4U0142, the anomalous X-ray pulsar, in showing its spectrum and its turnover and its upper limits with the Compton upper limits, and you see that these models do not, as they are, from single field loops, do not match that. Okay? You see large drops, resonant regimes, spikes, then non-resonant interactions, strongly resonant interactions, and all of this stuff up here will get reprocessed because we're very close to the surface. Okay? Above 1 MeV, thank you. It will be reprocessed by, actually by pair creation. Okay? Below 1 MeV, photon splitting can take out the extraordinary mode down to even about 50 keV. That's a project that my new graduate student, Kun Hu, is working on. And it's early days yet, but we'll get some results on that fairly soon. And we'll be able to see what the attenuation probabilities are here. And so these photons will get reprocessed. And that's got to be included in the full model, which has to be modeled by a magnetospheric cascade. Okay? Now, variability. So, okay, so if you take those, the right-hand portion of those peaks, sorry, wrong way. Okay. We have just lost our, okay, there we go, it's sensitive. Okay, if we take the right portion of the peaks here and say, this is our maximum energy from the resonant range. Okay, we take that energy and we say, okay, let's plot it as a function of pulse phase. So now we're taking our theta viewing angle, theta v, is now varying as a function of pulse phase, which is shown here on the x-axis. And we're taking a log of the photon energy there. Here it's 0, it's 0.51, so that's 5 MeV. That is 511 keV down here, so 1 MeV is about here. And we have these curves that are oscillating. Let's take this case where we've got the inclination angle between the magnetic field axis and the rotation axis is 60 degrees, the so-called alpha angle. And you see these large oscillations here, and these oscillations are labeled by different values of a parameter which amounts to different values of the observer's viewing angle zeta in pulsar speed. In other words, the angle between the observer's viewing direction and the actual rotation axis. And you see these large changes. In the upper portion, we've got light contours here because this actually doesn't correspond to resonant emission. It corresponds to non-resonant emission or low resonant emission, deep in sampling deep into the the exponential tail of the surface thermal Planck spectrum. So this is not very luminous, so you're really only going to detect this type of stuff. Pair creation and photon splitting is also going to get rid of these photons, these energies, so you're going to see some sort of profile that will do that. The profile depends on alpha, whether it's 30, 60, or 90. You can see vast changes, vastly different changes. So we have the possibility that with this type of study, we'll be able to measure the inclination angle. And if we can measure the inclination angle, we can actually retrofit what is out. We measure the dipole moment times the sine alpha when we do spin down, so we can actually measure the magnetic field better. Okay. Spectra are polarized. That speaks to the sorts of information, the stuff that both Robertos were talking about. When we integrate over a whole bunch of field lines, let's pick a field line and say we have one value of the maximum radius. Then we take all the azimuthal angles as we add up around a sphere, so around the magnetosphere. So what we've got is a toroidal field surface. Okay? If we integrate over that, the stuff where the magnetic field plane cuts the line of sight to the observer, it gives you the hardest emission. Everywhere else is softer. When you add that up, you generally get, by and large, with the exception of when you're looking down the magnetic pole, you get these spectra that are steepened somewhat. Okay, they're steepened, now they're now flat. Okay, so they're now e to the 0. Still doesn't match the data. We've worked at this of how to add up over this. It's not easy to do, to add up over a bunch of different toroidal field surfaces with different R maxes. And we find that the low R maxes give you the hardest emission, but they tend to be fairly low and up at the highest energies, and the small R maxes, the high R maxes at high altitudes tend to give you soft emission, but a large amplitude. And so it tends to give you a spectrum that is not too far from the actual reality of the data. But we're not generating that with any, we're waiting to see, put the cooling in before we actually really explore that in great detail, because the results will depend on self-consistent inclusion of the resonant cooling as the particles go around the field loop. But it's an encouraging sign, okay, that we will actually step into the form. We will need photon splitting and pair creation to get rid of these photons in order to be able to accommodate the Comptel upper limits. Again, these plots are for different viewing angles, instantaneous viewing angles. Okay, so to wrap up, we've sort of got a very good suite now of what we believe are robust spectral templates for what is produced for resonant Compton upscattering, inverse Compton scattering in strong magnetic fields to model magnetar hard X-ray tails. They are strongly dependent on the observer perspective, on the electron Lorentz factor, and on the emission locale. And what you get depends on how you add them up. A lot of the phase space, we can actually meet the Comptel upper bounds, but a lot of the phase space, we can't. Okay? Particularly if we actually sample the field lines that are in the plane pointing towards an observer. And we don't really know what the activation is. It's not going to be uniform. It's not going to be a uniform distribution of field line foot point colatitudes or field line foot point azimuths. So we really think that we're going to need pair creation and photon splitting to get rid of the gamma rays and the hardest X-rays. Next step is to actually put the cooling that we've done together with the Compton upscattering spectral studies together. And the best way to do that, I think, is with a Monte Carlo simulation. And we have a lot of those elements actually in place through other projects that we've worked on over the years. We can also do, to a considerable extent, we can actually test it, do code validation with kinetic equations. The output, what we want is to do is phase resolve spectra with polarizations, because the process is naturally polarization, and then it can be folded into the stuff that both Robertos are talking about in terms of the vacuum birefringes, propagate to infinity to see the observer. So in terms of agendas, where we want to set the scene for future Compton polarimeters. Okay, so this is now not IXP or XITE, but actually at the higher energy band above 10 keV. Systems like POET or eAstrogam, where you with the sensitivity to be able to probe the tail pulse profile at different energies above, say, around 30 keV, and then we can probe magnetospheric physics and geometry. Thank you.
Thank you, Matthew. There is time for a couple of questions. Ali, please.
Matthew, what happens for higher multiple surface fields?
Okay, everything we've done is for dipole. Okay, so all the kinematics, the kinematical information would be treated on the same footing. The geometry would be different. Okay, so what we want to do is, for example, if we were to say, let's take a toroidal component, the simplest thing, say, put a magnetic field that's a toroid instead of a dipole. Okay, that's the simplest generalization to sort of test this. Okay, that changes the plane of all your information by 90 degrees. Okay, so that means the polarization signals will change. They'll be the same magnitude, but they will change. The field will go up in amplitude, so you will push more towards the higher field results, which tend to be harder. Your viewing point will be, hey, if I'm like, instead of saying I'm along a magnetic dipole axis gives me the greatest Doppler boosting, it will be equatorial planes will pick up the greater Doppler boosting. Okay, so that you can sort of see you get a mélange, a mixture of information if you put the two together. And what you get will depend on how you do that complicated geometry when you do field line twists or even multipole moments. And so there's no clear answer to it. We have a sort of a general idea of what we might get, but there's no, it depends on what you put in.
Other questions, comments? May I ask a question?
Mm-hmm.
Did you actually consider to put in a particle velocity distribution? Or this was just for constant gamma?
These were, yeah, I neglected to say these are monoenergetic, okay? The reason we could do that, what it does is it smears out the results, okay? So you can have a convolution. The point, you can put that in, but that's the whole point of doing the self-consistent cooling, because that generates, instead of just putting in some distribution, you're actually generating the correct distribution for whatever your magnetic field geometry is. And that's best done with a Monte Carlo. So that is our next step.
Okay. Thanks, Matthew,
Okay.
again. And
Thank you.
And the next and last speaker for today's session is Sergei Popov, who is going to tell us about the surface magnetic field structure and the whole evolution in the crust.
Okay, good evening. So I'm going to speak a little bit about magnetic field evolution, magnetic field decay. On Thursday, you'll hear two talks by Sophie Harp and Pires about diversity of neutron stars and their evolution, so I will not stop on it, but definitely you already heard that there are many different types of young neutron stars, and it would be nice to merge them in one evolutional picture. And such program, such framework is going on, and the main thing to explain this diversity and connections between different types of neutron stars is the magnetic field. So three main ingredients of such a unified model, which hopefully can explain everything. They are all related to the field. The first is, of course, the field decay. It does not only explain the evolution of magnetars, which are definitely living on magnetic field energy, but it also helps to explain, for example, X-ray dim isolated neutron stars, this Magnificent Seven, which are most probably remnants of magnetars. The next ingredient which is important to explain things is the opposite process, is the process of emerging magnetic field. Also already in previous talks we heard that after an episode of strong fallback, field can be covered by a layer of matter, and then it slowly diffuses out, and it helps to link, for example, central compact objects with the rest of population, I would say. And finally, the magnetic field topology is very important, and in particular, toroidal field is very important. As for the decay, there are many evidences. Typically, we hear about isolated neutron stars, magnetars, and well, especially magnetars, but just to give some extra illustrations, it is possible to probe the magnetic field evolution on a longer time scale, on a time scale of millions or maybe few tens of millions years, because we have high mass X-ray binaries, which are definitely not older, because massive companions simply don't survive for 100 million years, for example. And also the accretion rate is not high enough to really significantly influence the field evolution. And if you take spin parameters of a large population of high mass X-ray binaries, you can try, using modern models, derive the magnetic field distribution out of it and compare it with predictions of models designed for magnetars. So, and on the left figure, you see it. So we start with something shown with a dashed line, then magnetic field evolve, and it comes to the distribution shown with a solid line, so you don't have high magnetic field contribution, and the crosses shows what comes out from the data on high mass X-ray binaries. So there is nice correspondence. Indeed, in high mass X-ray binaries, we don't see candidates for highly magnetized neutron stars. Maybe just now there are some candidates which people think can be accreting magnetars, but in my opinion, it can be better explained in the other way. What about normal radio pulsars? Do we see field decay in normal radio pulsars? That's a very tricky thing. There are many different, typically population studies. In some, I would say most of them, people don't see any strong evidence for magnetic field decay in normal radio pulsars. In our opinion, typically it happens because people study the whole population on a long time scale. And the answer is that normal radio pulsars, so neutron stars with fields like 10 to 12 Gauss, they don't experience significant magnetic field evolution on a very long time scale, so a few million years and more. Andrei Goshev few years ago suggested a more, I would say, sophisticated way to probe it, and after we applied this approach to some set of pulsars with well-defined data, we found that in a very narrow range of ages, I would say several 100,000 years, we see strong evidence for moderate magnetic field decay. The field is normalized to the initial value, so the field decays slightly less than a factor of 2 in several thousand years. And can I do it? Yes. So the typical time scale corresponds to this value. And then, of course, we cannot continue this decay for a longer time scale, because then pulsars would disappear and the PP dot diagram would look significantly different from what we have. So we have to stop field decay somewhere here at the age about 1 million year at most. And that's an interesting thing, how to do it. It depends on the answer on the question what kind of decay we see. Either it is just a pure ohmic decay on phonons, which exist in the crust till it is hot enough, when the temperature is above a few tens of million Kelvin. Or the most important ingredient which drives the magnetic field evolution is the whole cascade, which normally is working in magnetars, but of course it can exist also in less magnetized neutron stars. Simply the time scale would be longer. For the whole cascade, there are several. I'm doing something wrong with it. Чем вот этим? Okay, thank you. There are several numerical models for the whole cascade, and the interesting feature which appeared just a few years ago, at first in the paper by Gurguliatis coming in 2013, that after some time the field configuration comes to some stable configuration, and the whole cascade is not important anymore, and this stage was called by these authors the Hall attractor. And this is quite an interesting prediction. And of course, it's interesting to pinpoint it in some real population of neutron stars. And at first, our idea was that probably we see that neutron stars appear at the stage of Hall attractor, and we can see it in normal radio pulsars. There are predictions about field configuration, but for radio pulsars, it's not that important. I will show this slide once again later. It's important that there are independent studies of the magnetic field evolution, which confirms the idea of the Hall attractor. So that's another result by a different group of people. Do we see a Hall attractor in normal radio pulsars? We can play with parameters inside the neutron star. I don't have time to stop on it. We need thermal evolution because the field decay on phonons depends on the temperature, and we used cooling curves calculated by St. Petersburg group. And for parameters we are interested in, the whole time scale, the whole cascade time scale is comparable with the time scale for ohmic decay due to phonons. So this line is for phonons. This is h. This is the time scale. It increases because the neutron star is cooling down. And these lines are whole time scales for different initial magnetic field. This is a very long time scale for ohmic decay and impurities. We can put all these ingredients, impurities, phonons, whole cascade, and see what happens when we, at some age, we switch off phonons when the neutron star crust reaches some critical temperature, and then we can switch off the whole cascade according to predictions of numerical models. So we can show it all together. Field is normalized to the initial value. Here, everything goes on and the field decays significantly, so it doesn't look realistic, it doesn't work. Here, there is no whole cascade at all, and what happens is that phonons are not important anymore after the critical temperature is reached, and it looks like this is working. So the whole cascade, if we believe in numerical models, is switched off in normal radio pulsars too late, at few million years, and the field already decays by a factor of 3 or 4, which doesn't fit our results. So unfortunately, we were not able to see the whole attractor in normal radio pulsars. We can plot tracks on PP dot diagram, and to see the whole cascade, the whole attractor for normal radio pulsars, you have to be here, and there are very few pulsars observed here. But maybe there are other sources. And these lines, they correspond to field decay due to whole cascade by a factor of so 2 E-folds and 3 E-folds. And these green symbols are the Magnificent Seven. And it looks like they might be close to the whole cascade, according to the whole attractor, sorry, according to numerical models, because the field decayed by nearly an order of magnitude, so they started here and then passed through the magnetar stage, maybe it came here. So they can be good candidates to look for the for objects on the whole attractor. We can choose the best of them. Here is the magnetic field luminosity. It seems that stars which are closer to the whole attractor might be more evolved, more relaxed, so they might have lower luminosity, definitely, because there is less field decay inside them, and probably lower field. So we have to look for objects here. Luckily, 1856 is here. It's the first and the best studied, maybe, neutron star among the Magnificent Seven, so we focus on it. Then I come back to this slide. There is a prediction for the Hall attractor from Gurgulatas coming. The magnetic field on the stage of the Hall attractor should be formed of the dipole and the octopole of the opposite polarity. Here it's of the opposite polarity, plus some contribution from the next multiple L5. So here they are, how it looks like. Roberto Taverna calculated temperature maps for 3 cases. For dipole plus octopole, we call it model 1, dipole, octopole, and the small contribution L5, and as a reference model, of course, we use pure dipole. The main feature is obvious. The hot region is larger for neutron stars on the stage of the Hall attractor. And as we are going to see in next slides, it actually kills everything. So unfortunately, the model doesn't fit. So when we just fit spectral data, it's fine. We can also play with the effects of the surface. Everything is fine, but we come to the point which doesn't fit. We can calculate, we can fit the spectrum with a 2 black body model and look at the parameters. These 2D plots depends on these angles which were shown before, angle between the line of sight and the rotational axis and the magnetic field axis, or the dipole axis and the rotational axis. And we see that normally for 2 models which corresponds to the Hall attractor, the hot part of the neutron star is larger, which contradicts to the observational data. And this is a very bad news for this idea. Pulse fraction is all right, temperature ratio is all right, but this wrong area ratio is a bad thing. This is the observational data to black body feed for 1856. And obviously we see that the hot part in this feed has smaller characteristic radius, and the cold part has larger characteristic radius. What we expect normally, there is some small hot area and a larger cool surface, but best fit models for model 1 and model 2 give the opposite result, and so unfortunately, even in this case, we at least don't see any correspondence between the prediction of the model for the Hall attractor, for the model of the magnetic field topology, which is reflected in the temperature map, and results of observation of the source, which seems to be close to that stage if it exists in nature. So to give you some positive result at the end, or at least puzzling byproduct, when we discuss different members of the Magnificent Seven set of neutron stars, we see a funny thing. So there are 2 well-known sources, 1856 and 0720, and for both of them, kinematic ages are estimated, and the kinematic age is larger for 0720. But 1856 looks like more relaxed. It has lower luminosity, it doesn't have any peculiar behavior, and probably it is a hint to the fact that magnetic field evolution can be different for different stars, for different initial magnetic fields. So normally when we model, we put the same law of magnetic field evolution for all initial fields. So parameters can be scaled, but we don't expect that evolutionary tracks on the PP dot diagrams cross. And here probably it looks like, if we believe in all data, in particular, we believe that kinematic ages are really representative for real ages of the stars. Then the evolutionary tracks must cross on the PP dot diagram. That would be an interesting thing. And of course, thing that makes our life less easy. Okay, here I come to my conclusions. Unfortunately, we were not able to find evidence for the Hall attractor looking at the population of radio pulsars, normal radio pulsars, or looking at particular sources among the Magnificent Seven. So probably if the attractor existed, it is reached later, and simply the sources we could study are not at this stage yet, or probably this stage doesn't exist. Then there is a problem. We have to stop the decay somehow, and it would be very nice to have such a stage. And that's it. So I just leave it with the references. Thank you.
Thanks, Sergei. There is time for questions and comments. Ali.
Just a general comment, not really about Sergei's talk, is if you want to take some parameter as a unifying factor, there is the possibility, as I've been saying, that there's angular momentum in fallback material, fallback disks, which can explain why AXPs and SGRs, as well as the extents, have same kinds of periods. And now that people start talk again about fallback material, just to have a reason why the field is first buried and grow, it is more likely that fallback material has angular momentum, and therefore it doesn't fall back spherically to bury the field. It's just there to store the angular momentum, and then we get back. One can explain a lot of things like these anomalous breaking indices, what looks like field decay, etc., just by allowing the fact that there's some fallback material with angular momentum.
Are there other questions? Okay, if not, let's thank Sergei and all the speakers for this last session again. And we will reconvene tomorrow morning at 9.